Alright, so the next step for total internal reflection is we are also going to see what is the total or the net field like on either side of the boundary. On the input on the medium 1 side, we will find that the net electric field is essentially the sum total of the incident and the reflected fields. And since all of the power that is incident is being reflected, we will notice that we will see perfect standing waves with points where the electric field goes to 0, right? So this is the same situation. You can sort of go back uh, to when we studied reflections from purely reactive loads on transmission lines, right? Okay. So going back to our TM case, we can look at the x component of the electric field. We can say that it is E naught kxix e to the minus j kziz, right, plus gamma times E naught So since I am looking at only the x component, remember that it's not just the net electric field magnitude but the component that's aligned to it. So Ex naught, remember, would be E naught times either cos or sine theta, right? So you can go back to our original diagrams to identify that, but we are just keeping track of the x component, because remember the x component is what is used for the wave impedance, right? So we can call this Ex0R, but I'm using gamma already, right? So this is gamma times Ex of 0 e to the minus j kxix, because kxi and kxr is the same, right? We are in the same medium, and we have e to the plus j kz r z. Right, since kxr is equal to kxi, kzr is also kzi, right? Because the net k vector magnitude is the same. So we can remove this kzr and make this kzi. So let's take the common factors out. So we have ex0 e to the minus j kxi x. We have e to the minus j kzi z plus gamma e to the plus j z. Right, but we know gamma is 1 e to the j 2 phi tm. Okay, so we are going to take e to the j phi tm out, e to the minus j kzi z e to the minus j phi tm plus e to the plus j kzi z e to the j phi tm. Okay, so we are getting it of the form e to the plus something and plus e to the minus something. So we get a cosine relation, right? So using the Euler expression or the Euler formula, we can say that this is 2 ex naught e to the minus j kxi x e to the j phi tm cosine kzi z plus phi tm. Okay, so if we were to quickly look at this, so if I were to plot just Ex, the magnitude of Ex, right? So it starts off at some point, right? So this point is 2 Ex 0 cos phi tm, right? So at the boundary z equals 0, right? So if I put z equals 0 in this expression, and if I just look at the modulus, right, or the field amplitude, all the phase terms go away, and the cosine of kzi plus phi tm just becomes cosine of phi tm, and then we'll have standing waves in medium 1, right? So remember, this is medium 1 with epsilon 1 mu 1, and this is epsilon 2 mu 2 when we have total internal reflection, right? Because the reflected beam has all the same strength as the incident beam, right? The electric fields, they are able to completely cancel each other at certain points, right? So we are finding perfect cancellation, right? At these very specific z values. What can we say is the distance between these nulls? It is when kziz goes over half a rotation, right? So remember that cosine curve goes to 0 twice, right, in a full cycle, one at 90 degrees and the other at 270 degrees, right? So whenever kziz plus phi tm, remember phi tm is a fixed number. Once I decide what my incident angle theta I is, phi tm is a fixed number, right? So phi tm only depends on the material parameters and the incident angle, okay? So once the incident angle and the material is given to you and the definition of the boundary, then we can expect to see periodic positions of nulls, right? So you can say that the distance between the nulls is pi by kzi. Right? So now let us take a look at what the field looks like inside the second medium. We said that the amplitude would decay in the second medium, but let's find out the exact expressions, yeah, quantitatively, to find out what the electric fields in medium 2 looks like. So in medium 2, we can say that Ex t is t times Ex 0 kxtx and kzt z, right? But we know kzt is minus of j alpha z. Okay, and so remember also that t is 1 plus gamma, and we have ex0 e to the minus alpha z z e to the minus jkxt x. So you can see that the amplitude is decaying now into the medium. So 1 plus gamma can be written as 1 plus e to the j 2 phi tm, right? And this can be quite simply written as, if I take e to the j phi tm outside, this is simply 2 cos phi tm ex0 e to the minus alpha z e to the minus j kxt x e to the j phi tm, right? So if we were to look at this to add to our figure from the previous slide, so this is our z equals 0, and we plotted a cosine curve, right? So this was region 1 with a maximum value of 2ex naught, and this point at the interface was 2ex naught cosine of phi tm. Okay, so here also we find that if I were to just plot the modulus, right, these terms will go away and I am only left with this, and if I were to put z equals 0, I see that the boundary conditions match, right? The amplitude is 2ex0 cos phi tm, it's the same, but as I go to further and further positive z's, I essentially get an exponential tail, right? Okay, so I highly encourage students to also try out the total internal reflection case for the perpendicular polarization, right, and ensure that you understand where the electric fields become a maxima and where do you find the nulls, and how does this electric field value change as we move into medium 2, right. So what is key or important to see in all this, right, is yes, it is quite a lot of mathematics in doing the derivation, but nonetheless the concepts, the underlying concepts are highly important, right. All right, a final parting comment before we move to a very special boundary case is to say that as students you are also equipped at this point to even deal with arbitrary polarizations that are launched into dielectric boundaries, right. So you can always decompose any arbitrary polarization into the parallel and perpendicular components, and for each of them you can treat them as plane waves with a linear polarization that is either parallel or perpendicular to the angle of incidence, the plane of incidence, right, and you know how to evaluate the Fresnel coefficients, right, be it less than the critical angle or more than the critical angle, or in the case of going from a rarer to denser medium, for all angles you should have the necessary mathematical toolbox in order to estimate various things, right? So technically, if I gave you a plane wave interaction with a dielectric boundary of arbitrary polarization, you should first know how to decompose it into the two parallel and perpendicular polarizations. You should be able to immediately tell me the reflected and transmitted angles. You should be able to use the Snell's relations to get that. You should be able to identify how much of the light is reflected and how much is transmitted for each of the two polarizations, and then you can combine the two orthogonal polarizations to find out what has happened to the polarization state after having interacted with the boundary, right? And you will notice that in the most general case, since the field reflection coefficients are not the same for parallel and perpendicular polarizations, you expect to see a change in the state of polarization after interaction with the boundary, right? This is in the most general prediction. There may be very specific cases like in the normal incidence or at certain specific properties, right? So I can set up the properties of the media in such a way that we can ensure certain kind of polarizations are reflected or transmitted, right? And I can also choose, say for example, if I use the Brewster's angle, I know for a fact that the reflected beam is going to be highly polarized, right? And this hopefully also solves the mystery of the very first experiment that I showed at the beginning of last week, right?